Okay, so let's get started. Let me share my screen. Uh, okay, can you see my screen?
Yes.
And definitions. Okay, so therefore last class we are looking this definition and then we ran out of time. So I like to continue from the next slide. So everybody say this is stability phenomenon. So as you can see, I have written down a equation like del t equals to Ts del delta plus Td del omega. So, and what I have written on top of that, with electric power system, the change in electrical torque of a synchronous machine following a perturbation can be resolved into two components. So you all know about that, the T is the electrical torque and electrical torque is the multiplication of electric output power phi multiplied by the omega. No, sorry, electric output power divided by omega. That is the definition of electrical torque. And that torque, when there is any change in the torque due to any disturbance, whether it is a small disturbance or large disturbance, it can be decomposed into two components. One is that Ts del delta plus Td del delta. So where you can see the symbol, Ts stands for synchronizing torque coefficient. Td stands for damping torque coefficient. And del omega represents the speed deviation or speed change. Del delta represents the rotor angle change or rotor angle deviation. So therefore, once there is any change in electrical torque due to any disturbance, it can be decomposed into two components. So the first component is the component of torque change, which is in phase with the rotor angle, and that is called the synchronizing torque component. The remaining one, the next one is called the damping torque component, because this is the component of that electrical torque which is in phase with the speed deviation. So now depending on situation, you can understand the whether the system is going in stable position or unstable position. So therefore, for example, I have explained this equation in the next slide with the help of our diagram. Let me zoom in a little bit. So everybody see, I am showing like four responses. At the leftmost side, you see del delta versus t, del delta t, del delta t. Look the leftmost, I mean the responses. It is oscillating, but gradually decreasing. At some point, it is fine. So this means this is the example of stable system. And in this case, you see the diagram, phasor diagram right side, x-axis del delta and y-axis del omega. And what I have written in the middle column, stable means both Ts and Td are positive. You see that for del Ts and then del Td, and the resultant is that del Ta. So if both are in the positive direction, then the system is stable. And that's why, see the leftmost side, you got this type of response. That is the meaning. But see the next one. First look the leftmost side. It like going outward and oscillating, and then finally it is going out of state. It did not come back. So this is the example of instability or unstable situation. And why it happened? Now see the right side, the phasor diagram. In this case, del TD is fine. It is still on the positive side upward. But you see the del TS, it has been on the negative side. So that's why I have written negative TS, positive TD. This means TS is that synchronizing torque coefficient. This means in the system, if there is no proper or enough synchronizing torque, then the system will go unstable. It will be fully pull out or stepped out. That is the meaning. And it is called non-oscillatory instability. Because you see, although it started oscillating, but then it is not oscillating, it just went out of step. That's why it is called non-oscillatory instability. And then as I have given the caption, with constant field voltage, we are assuming that in the system, field voltage is constant. Now, the bottom two figures, you see the caption I have said with excitation control, meaning that the field voltage is not constant. We are controlling the excitation circuit, but still there can be similar situation, stable case, unstable case. So therefore, see this figure. Again, it is very similar to the first case. System came back to oscillate, the stable condition after some oscillation. This meant in this case again, both TS and TD is positive. So the thing is that if any of the two are the negative, then the system will be unstable. For example, in this case, you see, the TS is fine. It was in the positive direction, but delta has been now downside. This means negative side. And then you look the response. It started with a small amplitude, but then gradually increasing, and increasing, you don't know, and then system will be unstable. And it is oscillating. System is not going out of step like the second case. You see, second case like here it ended. It went fully upward side and then fully lost here. Never came back. But it is like it is going and then gradually it will increase magnitude. Yeah. So it is the oscillatory instability. This is also the example of unstable situation, but oscillatory. And second one is called non-oscillatory. So what is the reason of this oscillatory instability? Why it is oscillating? Due to lack of damping torque. So that's why the damping torque has been negative. That is the meaning. And in this case, what is the reason of non-oscillatory instability? Due to lack of sufficient synchronizing torque. Therefore, this is the difference. In this case, there is no good damper. System was not getting damping, gradually it is exaggerating. It is increasing. In this case, it is not like that. After some time, it fully step out. And this means there is no proper synchronism. Synchronism is not being maintained in the system. So synchronism means to maintain the appropriate frequency, speed, and voltage. That is the reason. And in this case, there is some issue with some control action. That's why it is not providing proper damping. That's why it is oscillating, but it has been unstable. This waveform is not accepted. That is the meaning. So that's why uh, these four plots are mathematically represented with the help of this equation. That is the meaning. So therefore, I have like summarized, oscillatory instability is due to lack of sufficient damping torque and unstable control action. Even though some damper might torque, but in the network there are many control system. One of the control system has been unstable, and that is causing oscillatory instability. And non-oscillatory instability means that is the lack of sufficient synchronizing torque. So therefore, you will be keeping these 2 points in mind. Okay, so moving forward, there are some other pretty standard definition. For example, everybody see, what is the meaning of transient stability? So transient stability, it is the ability of the power system to maintain synchronism when subjected to a severe transient disturbance. Then what was the severe transient disturbance? Faults on transmission lines, sudden increase or decrease of large loads. So that is the transient stability. So therefore, what is the difference between transient stability and small signal or steady state stability? Transient stability, when it is the severe transient disturbance, major fault, major disturbance. Steady state stability or small signal stability due to small change, like a small change in load or a small change in generation. Those are the cause of small signal stability. Therefore, other two standard terms that you need to know, one is called transient stability limit. So what does that mean? we understood transient stability, but what does that stability limit mean? So transient stability limit refers to the maximum flow of power possible through a point in the system without the loss of stability when a sudden disturbance occurs. This means that you know that transient stability means issue of major disturbance, and at that time under that disturbance what happens, huge current flows in the network. Therefore at some point, at some portion of the network, power flow could be very high, power flow could be maximum. So therefore transient stability limit means what is the allowable or what is the permissible or maximum value of power that is possible to flow through a particular point in the system without the loss of stability. This means if the power flow goes beyond that point, beyond that power value, then the system will be unstable. That's why it is called the transient stability limit. This means until that point, system will be stable, system will come back. After, if the power flow is too much, then the system will lose synchronism. System stability will not be maintained. That is the definition of transient stability limit. Now, other term, critical clearing time, it is called CCT. The critical clearing time means the maximum time between the fault initiation and its clearing such that the power system is transiently stable. And this includes the relay and breaker operating times and possibly the time elapsed for the trip signal to reach the other end of the breaker. And critical clearing times are in the range of few power frequency cycles in modern power system employing high-speed circuit breaker. Hello, did anybody say anything? Okay, I'm sorry. So therefore, what is the range of critical clearing time? It is like not that big value, only like few power frequency cycles, maybe only 2 cycle, 3 cycle, or 5 cycle maximum. And there are some high-speed circuit breaker, like on-cycle breaker in service, and some power electronics or solid-state relay. So therefore, regarding this critical clearing time, let me just stop this on and share my whiteboard. Uh, so therefore, you all know that, just a moment, let me. Okay, so this is the portion of a transmission line or distribution line, and then these symbols, these represent circuit breaker. For example, circuit breaker 1, here it is circuit breaker 2. And circuit breaker, you see, it looks like the switch. Basically, during normal conditions, they are in closed condition. They are in closed condition. And then the current is properly flowing through it. So therefore, what happens once there is a fault in the system, for example, some fault happened here along the line. This is the fault point. So therefore, what will happen? These circuit breakers will open. Immediately, these breakers will get open so that the faulty part is disconnected from rest of the network. So that is the function of the circuit breaker. Now, as I said that, initially it was closed, I'm closing again, the fault happened, but when does that breaker opens? So the breaker opening means fault clearing. As I remember, as I showed you, okay, that is the meaning, is that fault clearing. Now we are talking about that time. How long does it take after happening the fault to open the breaker? That is maximum 5 cycles. That is maximum 5 cycles of the waveform. For example, current was flowing, and this is the voltage waveform. or the current waveform. You all know this is on cycle. So, and this is on time period. So from here to here, that is t. So what is the distance? So that t equal to, you all know, t equal to 1 over f. So if you have calculator, you will find 1 over for United States, it is 60 hertz. You will be getting about 16.67 millisecond. If it is 50 hertz based system, then it will be like 1 over 50, you will be getting 20 millisecond. So that is called the duration of on power cycle. So what I am telling, that for 50 hertz based system, it could be that critical clearing time, CCT, it could be maximum 5 cycles. This means uh, 0.1 second. And in this case, you multiply by 5, probably it will be about 0.083 second. That is the time. So maximum 5 cycle. What is that duration? Initiation of the fault until the opening of the breaker. Because this breaker means it is dependent on protective relay, and there are triggering coil. So it needs some time. That time is maximum 5 cycles, not more than 5 cycles. I mean all over the world. Within that time frame, this circuit breaker must open to disconnect the faulty part. So that time is called the critical clearing time. If it is too longer, by then the system may be damaged, or there will be severe damage or the detrimental negative effect on the system. And then there are high-speed circuit breakers these days, which can open like at the like 1.5 cycle. This means 1.5 cycle. So this is on cycle, and then like 1.5. So what is that time? You can see like 30 millisecond. The circuit breaker can open, or like about 24 millisecond time. Circuit breaker can open. The maximum is 5 cycles. That time is called the critical clearing time. So everybody, could you follow me? What I am talking about?
Yes, Dr. Ali.
Yes, thank you. So this means I was discussing that critical clearing time. Yes, I was discussing these things. So therefore, look once again, critical clearing time is the maximum time between the fault initiation and its clearing, such that the power system is transiently stable. So that clearing means that opening that breaker. This means you cleared the fault, you disconnected the faulty part. And that time includes relay and breaker operating times, and possibly the time elapsed for the trip signal to reach the other circuit breaker. So that is the CCT. Now moving forward, couple of standard definition. Voltage stability. What does that mean? So voltage stability means it is the ability of a power system to maintain steady acceptable voltage at all buses in the system under normal operating conditions and after being subjected to a disturbance. This means that, I mean, so far we discussed steady state stability, rotor angle stability, transient stability. So although, I mean, voltage, frequency, all are included inherently inside the transient stability or steady stability, but still it is treated differently, voltage stability. So voltage stability means due to some disturbances, major disturbance, and due to small signal disturbances, if the voltage is maintained or voltage returns back within an acceptable limit, within an acceptable range at all the buses in the system, then we can say system is voltage stability maintaining. This means system is stable in terms of or with respect to the voltage. So this means that not only the rotor speed, not only the rotor angle should come back to the original position or acceptable position, voltage should also come back. Now, depending on situation, depending on system structure, it might happen that rotor angle came back, your speed came back, frequency came back, but voltage unfortunately did not come back. That is the voltage stability issue. That's why, I mean, in literature or in book or in many research articles, you will find that voltage stability is treated differently. But ultimately, all are like interrelated. All are the stability. Now, voltage collapse. You will find another terminology in the literature, voltage collapse, meaning that it is usually the result of a sequence of events accompanying voltage instability, leading to a low voltage profile in a significant part of the system. Voltage collapse means voltage has been so low, it has been very close to zero, and there is no chance of coming back. So the top on voltage stability means like after some oscillations, voltage will come back. Voltage collapse means it has gone close to zero and there is no chance of coming back. I mean, full breakdown, almost breakdown. So that's why the term voltage collapse. I mean, of course, this is voltage stability, but what I am telling that voltage stability means it will come back. Voltage collapse means it will not come back. Full voltage instability. What is the meaning of frequency stability? Again, the same thing. Frequency stability means due to small disturbance, due to large disturbance, if the frequency is maintained at a steady frequency level or at a certain level, then you can say this is the system is maintaining stability with respect to frequency. Therefore, again, it is treated differently, although it is interrelated, but sometimes it is completely a different chapter or a different stability because it has been seen in real practice. Although voltage came back, I mean, the power came back, reactive power is being maintained, rotor angle is being maintained, but still frequency did not come back to an acceptable limit. So that is the frequency stability issue. That's why each are being treated separately. Okay, then moving forward, uh, one important thing here you see I have written for you. In practical power system, small signal stability is largely a problem of insufficient damping of oscillation. And the stability of the following types of oscillation is of high concern. Local modes or machine system modes, inter-area modes, control modes, torsional modes. Therefore, you all will be remembering these terms. These four are the, I am explaining each of them. These four are the regions of some small signal stability problem, and that may cause insufficient damping. This means that it looks like in a system nothing has happened. There is no major disturbance, no major fault, no short circuit, no open circuit, nothing happened. You are not understanding anything, but still system might be unstable because of these reasons. You don't know. And these things happen internally. You cannot see any external fall, no storm, no tree has fallen, but still because of these reasons, system might be unstable. And these are called like the small signal stability problem. But that has severe impact on the system. So what does this means? Local modes or the machine modes. So therefore, once again, let me take you to that whiteboard. Ah, let me erase all of these things. Okay. So therefore, for example, for example, there is one generator here. This is one generator. And then this is another area. This is another. I mean, there can be many generators. Uh, Similarly, in this portion, there are many generators, for example, n number. And like both are connected in parallel, I'm assuming. And then again, these all are uh, connected in parallel, and then all are like interrelated through some lines. But this is one area, and then this side is another area. And then, for example, system is running fine, both area 1 and area 2. This is area 1, area 2. But for example, in area 1, one of the generator is facing some issue. Each generator has automatic voltage regulator, governor, power system stabilizer. There are primary controllers. Something happened, not properly tuned, or because of little oscillation, that is causing some problem to the whole system. And that has started, or it may happen in this side. Just one of the generator, this generator, or this generator, something happened, and that is swinging with respect to the rest of the system. That is called the local mode or local oscillation. This means it is not any major problem. It is not the problem on both sides, or even not on the connecting lines, just because one component is causing some issue. That is called the local mode problem. Then next comes inter-area oscillation. This means there has been some issue in this area, some issue in both sides, there are some issues. It is called the inter-area mode of oscillation. So you don't know which generator, in one generator, there has been some unstable control situation that may cause the impact on the overall system. Third one could be control modes. Now, for example, in the entire network, there are many controllers. Automatic voltage regulator, governor, power system stabilizer, voltage regulator, capacitor bank, static var compensator, other type of controller. Somewhere in one controller has been unstable due to improper setting or unstable parameter. That may cause the oscillation, and that is not visible. And then finally the torsional modes. So to understand the torsional mode, I need to show you one picture, then you will understand it. You see, I explained you the top three: local mode or machine system mode, inter-area mode, control mode, torsional modes. What does that mean? So therefore, see the next slide first, and then we will come back. Yes. Everybody see this picture? Can you see the first of all, this is a system. Is a Western machine model system. In this system, there are 10 generators, G1 through G10. And you see how they are connected, highly interconnected system. And generator G1 has 15,000 MVA rating. Generator 10 has 30,000 MVA rating. But what I am showing that each of these generators, they have the shaft. So you look, you will see the bottommost figure, turbine generator shaft model. Like you remember, I explained to you that you need two things. This is your generator and it has a shaft. So left side is fully the shaft and right side component is representing the exciter. Exciter means the DC excitation. So you see on the shaft, I mean, so far always I drew a like shaft, a cylinder type of shaft, but actually in real practice, it has several components. You see, HP means high pressure, IP means intermediate pressure, then low pressure A, low pressure B. The, for example, what does that means? As I told you that turbine rotates the shaft. With the help of turbine, shaft rotation is maintained. So now, for example, it's a gas turbine or it's a steam turbine. Initially, it has very high speed, not just that 3,600 or not just that 3000 RPM or 1800 RPM. It could be higher. That's why there are several stages on the real shaft system, and they all are like connected together. For example, there is a connection here, there is a connection here, there is a connection here, there is a connection. With the connection, actually, it moves. So that's why here the pressure is too high, then intermediate, here is the pressure is low. Now, what does that mean? For example, this system, uh, think one of the generator, any of the generator in the system, somewhere some fault happened on the network. So the impact will come on the generator. And then because generator is connected with this shaft, so what will happen? This shaft will start oscillating, start spinning. But then see the way they are connected, because they are connected together, so the movement will not be smooth. Always there will be some oscillation. Like I think I can give you a real example. Think about the train. Train has several or the many apartments, and then you see the how the train runs here, or making right turn or the left turn or making a curve. I think you understand what I mean, and you have noticed the connection, the similar thing. So therefore, if something happens on the network side, any of the places, then impact goes on the generator shaft. And because they are connected together, they are coupled together, therefore there will be some vibration or oscillation. Now, what we are discussing here in the previous slide, we were discussing, you see, in practical power system, a small signal stability is largely a problem of insufficient damping of oscillation. Now, due to some issue in the network, it is a small signal. There is no major fault, no disturbance, no thundering, no storm, nothing happened. But due to some reason, those shaft, those shaft or portion of the shaft were oscillating, and that may cause problem to the other portion of the network. That's why it is called the torsional mode. So therefore, you all will be remembering these four terms: local mode, inter-area mode, control mode, and torsional mode. These four modes or these four are the reasons of many small signal stability problem that might cause insufficient damping of oscillation. So everybody, could you follow me? So far it is fine?
Yes, we are
Okay,
fine, Dr. Ali.
thank you. So therefore, now here you see in this slide, yes, here I am summarizing this one, classification of stability. First is the, you see, power system stability. Now it is of three types. One is frequency stability, other one is voltage stability, and third one is rotor angle stability. And rotor angle stability is two types. One is called transient stability, other one is called small disturbance or small signal angle stability. And you see, I have written short term. So therefore, in case of rotor angle stability, both transient stability and small signal stability, those are short term. So what is the definition of short term? Below I have written point of interest is 0 to 10 seconds. And then I have written down the definition mid-term, long-term, because we are using those terms here. So mid-term means from 10 seconds to few minutes. Long-term means few minutes to tens of minutes, very long time. Now, always you will keep in mind, always transient stability, or in other word, rotor angle stability, the duration is 10 seconds. This means that within 10 seconds, if the system does not come back to stable condition, then that is problematic. System will be unstable. Therefore, this is very, very dangerous, this short-term one. Within this time, system should come back within a acceptable range or equilibrium position. Now, see the frequency stability, short-term, long-term. You see, this the example is long-term. For example, at your home, you are noticing every day, like one light, it is like blinking, blinking, blinking. Or in your kitchen area, the light, tube light is like blinking, blinking. It is not going out. It is powering you. You are getting light, but it is blinking, meaning that that is the example of long term. Now, how much is the blinking or the flickering? It depends on that. If it is small, then fine. If it is too much, that might cause stability problem. And then the voltage stability, it is two types: small disturbance stability, maybe large disturbance stability. And again, it can be two types: short term, long term. Now, for example, as short term you can understand due to any short circuit or open circuit or any of those fault, three-phase fault, two-phase fault, single line to fault. But long-term voltage stability, like you have voltage, you are getting voltage, like always there is some sort of fluctuation. That is the example of long-term. And you see, few minutes to tens, or even it might be several days or for a month, continuously the issue is going on, the voltage issue and frequency issue. But the rotor angle stability or transient stability, always it is short durated. This means within that time frame, 10 second, system must come back to the stable condition. Okay, so therefore, you see, there are lots of dedicated or very high quality references. The discussion that I made, that of course, first reference is the book that I am following, Power System Stability and Control, and of course there are other good books as well. And then second one is other book, and then the third one is other book. Probably many of you have studied in your undergrad. Number 4 as well. Number 5 is a journal paper. You can download it. It was published May 2004, and see there are at least 10 authors. All are very, very famous professor. I mean, in the power field. You know, first author was the Prabha Kundur. I mean, he was the writer of the book. But probably, you know, like he passed away 2 years back, unfortunately. Long time. He contributed a lot in power system. He was working at Hydro-Quebec in Canada. And then the last author, you know, Vijay Vital, he is a professor at Arizona State University. So all, and then David Hill is from Australia. Goran Anderson, probably he died. And Venkat Rajaraju from Iowa State University. So Claudia Canizers from University of Waterloo. Then Anjan Bose, he's from Washington State University. In that, all are the very famous professors, and they publish this paper, Definition and Classification of Power System Stability. So therefore, you might download this paper, or if you just look my slides, that will be fine. And then there was another report, but you see, it's I mean quite old, but very very famous. July 19 to propose terms and definition for power system stability. Anyway, so then moving forward a little bit, um, although I mean in this course mostly we will concentrate on transient stability, we will be looking various means, but steady state stability is also very important. We have to look its stability enhancement means. So there are three main components, three main controller in the system that can maintain the steady state stability. So therefore, once again, steady state stability means you are handling the small changes in the system. So what is the one component? Automatic voltage regulator, AVR. It maintains the generator terminal voltage by controlling the field excitation. What is the governor? It maintains the generator speed and hence frequency by controlling the fuel input to the prime mover. So two things, AVR controls the terminal voltage and governor controls the generator speed. Therefore, by controlling the fuel input, if it is nuclear, then control the nuclear. If it is coal-based, then control the coal. Steam turbine-based, then control that one. That is the meaning. And the automatic voltage regulator, you have to control the field excitation, DC fault, that we apply on the magnetic coils or the magnetic circuit. And then there is third component, it is called power system stabilizer, PSS. It suppresses or damps out low frequency oscillation in power network. For example, in a network like nothing happened, but continuously there is oscillation. Like you are measuring the power or voltage current at a particular portion of the network, and you are just looking, there is continuous oscillation. It is not like at zero position, continuous oscillating. It is not going high, it is not going low, but a sustained or persistent oscillation. So there is a device, power system stabilizer, that can dampen or mitigates that impact. So therefore, you will keep in mind, I will be asking you the one question in the upcoming midterm exam on what are the means to maintain steady state stability. Then you will be mentioning these 3 points. Okay, and then transient stability means, I mean, we all will be studying these things over the, throughout the semester as the days go. Today I am just giving you a highlight. So the transient stability means there are several, I think I have mentioned at least 10: dynamic braking resistor, fault current limiter, bridge type fault current limiter, superconducting magnetic energy storage, unified power flow controller, static VAR compensator, static synchronous compensator, thyristor control series capacitor, static synchronous series compensator, and thyristor switch capacitor. Therefore, I have mentioned here 10. Even there are much more, and sometimes there are combination. Now, here you see, I have mentioned in a particular way. Everybody keep in mind the top 5 like VR, FCL, BFCL, SMS, UPFC, they can control the active power. And then the bottom 5, SBC, STATCOM, TCSC, SSSC, and TSC, they can control the reactive power. So this means that depending on situation, depending on stability problem in the network, sometimes you need to control the active power, sometimes you need to control the reactive power, sometimes you need the combination of both. Therefore, if you read many literature, many journal articles, then you will notice some some org are using, for example, combination of VR and SBC or STAT. Some org are using SMS plus one of the component, or BFCL plus SBC in that way. So therefore, just keep in mind the top 5 can control the active power well, the bottom 5 control the reactive power. And then later we will see, I mean, as the days goes, reactive power control is very important for the network. I mean, while both are important, but reactive control worsen the situation. If you cannot control the reactive power, then there will be voltage collapse. Today, we are looking on terminology, voltage collapse. If you can properly control the reactive power by using any of these devices, then there will be voltage collapse situation. And that is the very dangerous situation. Okay, so therefore you got these names. Over the time we'll be covering. Then now, based on what we discussed so far, I have set up some questions for you. You need to answer these questions. So therefore, let me explain, and then everybody, do you have your pen and paper? You can write down at your pen and paper. I will be discussing these. This is the kind of the quiz type of questions, and then it will be done for today. I will not be covering the new topics today. Everybody see the first questions. Let me make it bigger. Everybody see, first question: due to a disturbance, the generators in a power network stepped out. What could be the reason behind this? This means that you are noticing that in a power network, there are generators, and those generators stepped out. So what could be the reason behind this? So what do you think? So has Manoj come?
Structurally, I mean.
So, oh yeah, okay. So could you answer these questions? So what could be the reason?
Loss of synchronism.
So sorry?
Loss of synchronism.
Yes. Loss of synchronism. This means
Yeah.
due to lack of sufficient synchronizing torque, because generator is stepped out. You remember I was showing you that that picture, this one. Non-oscillatory instability happened basically. That is the meaning. So very good that you all understood. So that is the region. So this means the region is lack of sufficient synchronizing torque, meaning that there is no proper synchronism in the system. Now see the next question. Due to a disturbance, the rotor angle response of a generator located in a power network oscillates around the steady state value, and gradually the magnitude of oscillation increases. What could be the reason behind this? So Sindhuja, can you answer this one? Sindhuja, are you looking the questions? Hello, could you hear me?
Instructor, we could hear you.
Okay, maybe Sindhuja is not connected or something. Anyway, so Amani, could you hear me? Amani?
Yes, Mr. Ali.
So what could be the answer for this question?
To be honest with you, I'm not sure.
So you see the read once again, the rotor angle response of a generator located in a power network oscillates around the steady state. This means around the x-axis it is oscillating, and then gradually the magnitude of oscillation increases. So what could be the reason behind this? So therefore, see this figure, see the bottommost on. Amani and everybody look the bottommost on. You see, it started oscillating and then gradually increasing. So this means what I have written, oscillatory instability. And what is the reason? See this one, oscillatory instability is due to lack of sufficient damping torque and unstable control action. So this is the answer. This is the due to lack of sufficient damping torque and unstable control action. So now read once again that what happened? It oscillates around the steady and gradually the magnitude of oscillation increases. What could be the reason? So the reason is lack of sufficient damping torque and unstable control action. I mean that, and you might explain differently, but that will be the appropriate or actual technical answer. That's why I'm showing you that slide here. So now do you understand, Amani?
Yes, sir. Thank you.
Okay, thank you. Yeah. So therefore, everybody please you see the answer. So although I'm asking Amani, but then everybody please be attentive. Now see question number 3. In practical power system, small signal stability is largely a problem of insufficient damping of oscillation. What are the main causes of those oscillations? Sindhuja, have you come back online? It looks like Sindhuja stepped out fully. Lakshmi? Hello, Naga.
Yes,
are you
Dr.
here?
Ali. Yeah, I am here.
Okay, so what could be the answer for question number 3? In practical power system,
It could be due to oscillations caused by torsional modes or control modes, inter-area modes that we discussed in previous slides.
exactly. That is the answer. So I think everybody see, we discussed these things here in this slide. Those 4 are the answers: local modes, inter-area modes, control modes, and torsional modes. That is the answer. So thank you. Now, the question number 4, at steady state, is the frequency always 60 Hertz in a power network? Explain your answer. So, Venkat, are you online?
Yes, sir.
So, what is the answer for question number 4? At steady state means there is no major disturbance, no fault, no short circuit. So, do you think the frequency is always 60 Hertz in a power network?
Uh,
I mean,
may go up and
we are
down.
talking about United States, so that's why I said 60 hertz. You might think other country as well, let's say 50 hertz. Do you think that always the frequency should be 50 hertz or in United 60 hertz always?
Yeah, it has to be maintained.
Okay, but you see, why I mention always that sometime it might be 60, but in real practice it is very difficult to maintain that exact number because always there is some sort of change, always some load change is being happen
Yeah. So
continuously.
there is a uh, there should be around 10 plus or minus 10%
Uh,
deviation.
Not plus minus 10%, plus minus 3%.
Yeah, yeah.
Yeah. So everybody keep in mind. So there is a frequency range. I mean, although as I said that because continuously loads are being changed, even though small change, 60 watt, 40 watt, whatever, and every house, everywhere that is happening, that has some impact. So frequency is not at all like 60 hertz exactly. But the question is if is it 55 hertz or 65 hertz? No. It is within, if it is within plus minus 3%, then you can say that frequency is safe for the device. Your device will not be interrupted. So therefore, the United States, the standard practice, standard range for frequency plus minus 3%. If it goes beyond that range, I mean the bottom side or upper side, then that is the problematic. So therefore, when I say explain your answer, meaning that answer is no, the frequency is not always 60 hertz in a power network because always there is some sort of change, load change in the system. Now, question number 5. Why is not AVR, that means automatic voltage regulator, used in induction generator system? So therefore, Kamana, can you answer this question? Question number 5.
I think AVR only control the DC excitation, and in
Yes.
case of
Yeah.
induction generator, it needs AC excitation.
No, in case of no, you don't have to use the term AC excitation. You have
Okay.
to say that in case of induction generator, it always requires reactive power from the system to produce magnetization. You remember, in case of induction, everybody listen to me. In case of induction generator, there are no physical magnetic poles. There are no. So that's why you have to create magnetization internally. That's why you need the reactive power support. And that is the reason AVR is not used because it, you see what we learned. I mean, see this one. Okay, see this slide. What I wrote, AVR maintains the generator terminal voltage by controlling the field excitation. That is the function of the AVR. So this means where it is used with the synchronous machine. Synchronous generator has the magnetic field. So you have to excite that, you have to control that. But in case of the induction generator, there are no physical magnetic pole. So you don't need to use any AVR. Whatever control with the help of capacitor or other mechanism. Now, do you understand, Kamana?
Yes, Dr. Ali. Thank
Yes.
you.
So therefore, I mean, you are almost there. Like you have to tell that induction generator does not have the AVR because it does not have physical magnetic poles. To create internal magnetization, it always draws reactive power from the system. But because there are no physical magnetic poles, so you don't need any control system like the AVR. So this means AVR is only for the synchronous generator. So you know that in the exam I will be asking you different way. Why is AVR used with the synchronous generator? You see, today I am asking in that way, but in the exam I will asking different way. So that's why like you have to understand these answers. Okay, this one, number 6. Why is not capacitor usually connected at the terminal of a synchronous generator? So Manoj, can you answer this question?
I think you explained while talking about the synchronous generator, but I forgot.
Okay, got it. Yeah. So this means you see capacitor, everybody see the capacitor is connected at the terminal of induction generator. Because I mean, when I was answering to question number 5, everybody see, I said that induction generators requires magnetization. It requires reactive power from the system to produce internal magnetization. And because induction generator requires reactive power, so there will be low lagging power factor AC. Now, to improve that power factor, to maintain a steady voltage, you need the capacitor. Now, the question, this means the capacitor is for the induction generator, not for the synchronous generator. Now, the thing is that to answer question number 6, you have to tell synchronous generator has no issue with low lagging power factor because synchronous generator does not depend on the reactive power consumption from the network. The synchronous generator has the physical magnetic poles that are powered by the DC excitation. So it does not, and also it has the AVR and it has the governor. So that's why its voltage is maintained properly. It does not draw any reactive power. That's why it does not have any low lagging power factor. Consequently, capacitor is not needed. So this means capacitor is not connected at the terminal of synchronous generator. So this means capacitor is connected at the terminal of induction generator. And then from question number 5, AVR is connected with the synchronous generator. I think everybody understands, right? Yes.
Excuse me, sir.
Yes.
So, like in the synchronous generator also, there should be power factor maintained always, right?
Yeah. So to maintain that power factor, there is AVR, the DC excitation. So
Okay.
you know that depending on the excitation, over excitation, under excitation, or normal excitation, power factor can be lagging, leading, and united.
Yeah,
So,
yes, sir.
yes, you remember. Yeah. So there is, I mean, proper mechanism. I
So it
mean,
is done through the field excitation.
yes,
Uh,
yes.
you
Power
mean that?
factor is maintained with the help of field excitation.
Yeah, yes, sir. Thank you, sir.
Okay, thanks. So I mean, everybody, although I am like particularly asking, okay, you tell, I am telling them, but you don't take other way. Just I am discussing, I am making you attentive. So, but the questions are for everybody. So everybody, please listen and you note down the answer because I will be asking you similar questions in the upcoming midterm exams as well as the final exams. And these are very, very vital questions. You all have to understand and I mean, for example, if you work in a power field in MLGW, frequently you will need to deal with these concepts or in any power industry. These are very, very vital questions. Okay, then question number 7, you see, in addition to number of poles and frequency, is there any other factor that determines the type of generator used in a power plant? You see that why I am mentioning these things like poles and frequency because speed is related to pole and frequency. Speed is 120 F over P, right? Yeah. So this means speed is related to pole frequency. And so are those two only factors that determine the type of generator choice in a power plant or could there be any other factor? I mean, the question is, will you choose a salient pole type of machine or non-salient pole? Will you choose a hydraulic turbine or steam turbine? How you will determine that?
Based on the type of plant we are using the generator
Yeah,
or the source
based,
of fuel.
yes, based on the geography, right? Based on the geography. For example, at the University of Memphis parking lot, will you install a hydraulic generator? No. Why? Because there is no water available. So therefore, it depends on the availability of the resources. Like you are right, the fuel input. Same thing. We will place a coal-based turbine? No, it depends on the availability of the coal or the gas, natural resources. So that's why, in addition to number of poles, there is other factor, for example, geographic location, availability of the fuel sources, that determine the type of generator used in a power plant. Now, question number 8. For a given voltage and power, explain the effect of low power factor on a power network. So therefore, what happens? So now again, Sindhuja, have you come back?
Yes, Dr. Ali, my internet is not stable at all. So, yeah.
Okay. So, but did you hear me? I mean, we are discussing the answer, or you lost? Yeah.
Not really. It's continuously disconnecting.
Oh, okay. So twice
Yeah, I will listen to it.
looking for you, and then I was expecting the answer from you, but so
Oh, sorry. I couldn't
that's
hear.
fine. That's fine. So now, please look question number 8, and then try to answer. For a given voltage and power, what is the impact of low power factor on a power network? Do you think that is there any issue of the low power factor on the power network, provided that your voltage and power are constant? Okay, so anyway, so therefore, who could Amani, could you answer this one? Amani, what could be the answer to question number 8? What could be the answer for question number 8? What is the impact?
I think the low power factor will affect the stability of the power network of the system.
So
If you don't have a good power factor, or the power factor is not as it should be, so the stability of the system, it will not be
I think
great.
the current will increase because the active power equals to VI cos phi.
yeah,
So
yeah.
if you have lesser cos phi, then voltage is constant, power is constant, then current will increase.
Yes. And what is the impact of that increasing current?
So if current increases, then there will be voltage drop
Okay.
and
Yes.
less active power, more reactive power.
Yes. Okay, so I mean, so you're right. So thank you. So therefore, for a moment, just let me, in a minute, let me clean up these things. So Sindhuja, are you now connected? Can you hear me now? I think again.
Yes, Dr. Ali.
Oh, okay. So now we are answering that question. For a given power and voltage, what is the impact of low power factor? That Manoj was answering, like he was right. So you see this equation, just think about the single phase system. P equal to VI cosine theta. This is the active power equation. This cosine theta, this is actually called the power factor. Yeah. So therefore, from this equation, let's derive the value of the I. So what is that I? Like P equal to P over V cos theta. Now, for example, think that there is a line, it has R, it has L, it has C, and then the current flowing is I along that line, and this is R, this is L, and then this is the C. Now, see first this equation, we are discussing what is the impact of having low power factor. So therefore, this cos theta is low power factor. And then we are assuming that P in the equation and V, those are the constant. Those are not changing. So therefore, see, what is the maximum value of cos theta? Cos theta can be maximum on and then the minimum value is 0, right? So therefore, that is the variation of cos theta. So assume that it is not 0, for example, very small value 0.1. So therefore, if P and V are constant, and if power factor is 0, then you will be getting some value. Then just an example. For example, you got 100 ampere, just a random example. And then once it is 0.2, then definitely the current value will be lower, right? And in that way, if you go upward, for example, 0.9, then again you will be getting lower current. So this means that as the power factor goes upwards, current value decreases. And what are these values? These are the like low power factor value. Low, the definition of low means typically below 0.8 or 0.7. Those are really the low power factor value. So the 0.9, 1.0, these are the like very good or the desired power factor. So this means, in other words, when the power factor is low, current value will be higher. So what is the impact of higher current? Just look this branch RLC. For example, you got higher value of current and then I square R. What is that I square R? Power loss. So that Manoj had explained, there will be higher power. Similarly, for this component, there will be I square XL, I square XC. Even the reactive power loss will be higher. And then because there is higher value of current in this line, think about the voltage at this point and think about the voltage at this point. Let's say this is VC point and this is V0 point. So of course the voltage, there will be much more voltage drop here because high current is flowing. So therefore all these components will cause voltage drop. On the other hand, when the power factor is higher, this means you have low value of current, there will be low loss, there will be low voltage drop. So these are the impact of the system. Sindhuja, could you follow me?
Yes, Dr. Ali.
Okay, thank you. That was the question number 8 and answer. Amani, is this fine now?
Yes, Dr. Moshe, thank you.
Yeah. I mean, this is the actual answer. I mean, indirectly that you said there will be stability issue, definitely, because there will be voltage drop, depending on very low value, there might be voltage collapse. So therefore, in some sense, your answer is right, voltage, the stability problem. But this is the actual thing that you expect. Now I answer that one. Going here again, this question. So now we have 2 more questions, then today you will be done. Okay. So question number 9, when controlling a synchronous generator and an induction generator, what are the main variables that should be taken care of? So Lakshmi, could you answer this question?
Yeah. Yes, Dr. Ali, it's voltage and frequency, I think.
So which one is for what? Frequency is for which generator and voltage is for what? I mean, your answer is, I mean, partially right. I mean, there is detailed answer, but partially right. But can
frequency is for synchronous generator and voltage is for induction generator.
Okay, yes, absolutely right. And then can you relate any other variables with regard to frequency and voltage? Voltage is dependent on what? And frequency is dependent on what? I mean, your answer is correct, but partially correct. There are other points that I am asking, detailed answer. That's why I said, what are the main variables? Means there are other variables. But that is right.
Hardly, I mean, I can't get the what I was not able to think the.
Okay. So therefore, so everybody say that when controlling synchronous generator, like as she mentioned, frequency was one factor. In case of synchronous generator, like you have to control the speed as well. And you see in the speed equation, if you see n equal to 120 f over p, right? So therefore, pole number is fixed, but speed is related to frequency. This means that other factor is the speed. So speed is one factor, frequency is other factor, and what else? If you see the swing equation, active power. So therefore, everybody now write down the answer. To control the synchronous generator, the main variables of interest are frequency, speed, and active power. Frequency, speed, active power. Now come back to induction generator. What Naga told, that's absolutely right, voltage. But voltage is dependent on reactive power. If there is much more reactive power, then there will be low voltage. Voltage might collapse down. And what is related to reactive power? Power factor. So therefore, everybody, voltage, reactive power, power factor. Those are the dominating factors for induction generator. So therefore, let me write down that on the whiteboard, so it will be fine to you. Those are the job market questions. For example, you are getting interviewed at industry, they will be asking you these questions. So let me write down here. For synchronous generator, and let me draw here induction generator. So therefore, for the synchronous generator, the variable that you have to control, as I said, active power, frequency, and speed. For induction generator, voltage, reactive power, and power factor. In other words, in case of synchronous generator, these three factors are kind of analogous. This means the active power control means speed control, and speed control means frequency control. In case of induction generator, these three components are like analogous. Voltage control means reactive power control means power factor control. Now this means these total 6 variables are very important to maintain the proper stability of the system. Now in a real power network, there could be, conventional power network mostly are synchronous generator. But think about the wind generator, they are based on the induction generator. Solar system, PV system does not have any rotating dynamics because it is static. So we are not taking into the point. We are talking about that has rotating mass, induction generator and synchronous generator. These 6 are the main variables. And especially these 3 are the main variables. Now you might argue that induction generator have also frequency, speed, and power. That's right. Similarly, synchronous generator has also voltage, reactive power, and power factor. That's right. But these 3 factors are the dominating. These 3 factors are dominating for this case. Now you see, here it is power, active power, here it is reactive power. But you see, like all are interrelated. This is P, and then this is Q, and they are interrelated. You see, theta, and then this is S. The apparent power. So therefore, if you see this diagram, so you will find that ultimately P and Q are interrelated with the help of power factor. But then here I have distinguished it. I did not mention power factor here. I did not mention voltage here. I have mentioned power factor and reactive power voltage here. This means that, for example, if your system has induction generator, first you have to control these 3 factors. If your system has this generator, first you have to control this. These 3 are the dominating factor. In this case, these 3 are the dominating factor. Meaning that if you don't properly control these 3 factors for induction generator, system might be unstable. Same thing, in case of synchronous generator, at first you have to control these 3 factors. If you don't, if you only control these 3, system might be unstable. Do you understand the order of dominance and the preference? I mean, all 6 are interrelated, but these 3 are specific for this one. This 3 is specific for this generator. Therefore, in other words, in a system, if you have both generator, you have to properly maintain all these 6 parameters to maintain proper stability. So, everybody fine?
Yes, Dr. Ali.
Okay, thank you. Yes. So now I think there is last question.
Dr. Ali, I have a question.
Sure.
So is it also related to the droop control?
Droop control is something different. A little bit different. Yeah. Droop control. I mean, droop control is mainly related to voltage and frequency control. That does not relate the like power factor or active power. Mainly related to the frequency and voltage.
Okay, Dr. Ali. Yeah, thank you.
Okay. Then the last question is, in a power network, you notice that the rotor angle, speed, and frequency are at steady state. However, the bus voltage are not within an acceptable state. Is this still a stability issue? Do you think that is still a stability issue? Like rotor angle, speed, frequency are fine at a certain range, at a steady state, but bus voltage are not within acceptable state. Is this a stability issue? So everybody see this slide, this one. Look the definition of voltage stability. Everybody read the voltage stability. This means that voltage stability means you have to maintain acceptable voltage at all buses in the system under normal operating condition and after being subjected to a disturbance. Now, if that is the definition of voltage stability, but here what I am telling, it is maintaining rotor angle stability, transient stability, frequency stability, because they are fine, but voltage are not unacceptable. So therefore the answer is yes. This is a stability issue. In particular, this is voltage stability issue. So do you understand?
Yes, definitely.
Yes. So everybody please note, write down the answers. So the answer is yes. This is still a stability issue because bus voltages are not, I mean, attained or has not reached an acceptable state. So this means still voltage are at low level. So this is the voltage stability issue. This means if you don't take care, if you don't pay attention, then system might be unstable fully. So this is the voltage stability issue. I mean, depending on situation, there might be voltage collapse. Okay, so therefore with that, today I don't have much more question. I mean, in that way, always I will be asking some questions, numerical problems. From next class, everybody please keep your calculator with you. Next class, we will be solving some numerical problem. Oh, the first of all, I think next class, Manoj, you will have a presentation, right?
Oh, yes, Dr. Ali. Yeah, I forgot.
Yeah. Okay, now I reminded you. So then
Sure.
Please be serious. After your presentation, like if you allow me time, if there is spare time, then I will be lecturing something.